Hello class, this is Tim Tomlanovich and welcome to Structural Analysis 2 again. So there's gonna be a two-part video series here on Learning Plan 2 on Chapter 5 of your book. So on this one here, we are doing calculating stress of building materials and calculating strain of building materials. Okay, so with that, so there are lecture sheets in Blackboard that I recommend you print out, key terms that you need to be familiarize yourself with to get through your homework and get through the quiz. Okay, so those are attached. It's called Structural Analysis LP2 Part 1 lecture sheet, and then this is lecture Part 1 lecture note, and then I'll have Part 2 same thing. Okay. So let's talk about normal stress. So when you look at an object, an unloaded spring here, compression, normal stress, basically means that the load right here, so let's make this a little thicker just so it's easier to see for you guys. This, oops, and we'll do that again. All right, normal stress. The load is perpendicular, the force vector is perpendicular to a surface area. So when you look, when it's in compression, what's happening to this spring? It is getting shorter. And in tension stress, as you look, again, the force vector, remember, this is the sense, this is the line of action. The line of action, it's perpendicular to that face. You're pulling it, so that means it's in tension. It gets longer. Okay, so compression, normal stress, we're squishing it. Tension, normal stress, we are pulling it apart. Again, the load is perpendicular to the face. So pay attention to, these are my senses of my force vectors. Okay, so if we look, a formula, force, you have tension or force compression. F in your textbook stands for force, or F. Okay. T stands for tension, subscript C stands for compression, or this is that term sigma, Greek letter sigma. It means the same thing. Okay. P, actual force, that is in pounds, divided by the perpendicular resisting area. So see this little thing here? That is a perpendicular sign. Does that look like? That looks like an AutoCAD function. Okay. So if you look here, your load is acting perpendicular to that face. Okay. The area is the cross-sectional area perpendicular to that load. Okay. And then this is typically square feet or square inches, or if we go to metric, kPa or kilonewtons per square meter. Okay, it's important that you understand the units. Okay, so that's normal stress. Again, if we just turn this sense around and we turn it, we just turn the sense 180 degrees, this goes into compression. Okay, if the senses are originally, then it's in tension. But again, the load is perpendicular to the resisting area. That's key. P over A. F equals P over A, or sigma equals P over A. Okay, so it's a really simple formula to memorize. All right, let's do an example. A short timber post supports an actual load of 10,000 pounds. So we know P equals 10,000 pounds. And where does that P come from? That P comes from your load tracing, that last learning plan. Okay, you need to, this is how you design. So this is how you're going to be designing columns. You need to figure out that load, P. P equals 10,000 pounds. The post is a Douglas fir 6x6 S4S, surface on all four sides with an actual cross-sectional dimension of 5.5 inches by 5.5 inches. So that's key to make sure you know the difference. Is it rough sawn or is it surface on four sides? Because that makes a difference in your area calculation. So our area is 5.5 inches times 5.5 inches, and that equals, so 5.5 squared, 30.25 square inches. So that area is this right here. That is 30.25 square inches. Determine the actual compressive stress that develops in the post. Okay. Tensile, or develop the actual compressive. I'm sorry, it says compressive. Okay. So now we know F, that's stress, C equals P divided by the area perpendicular to the load, when that equals 10,000 pounds divided by 30.25 square inches, and that equals 10,000 pounds divided by 30.25. And I get 330.578. So I'm just going to round it up to the nearest whole number. Oops, sorry. Hit the button. 331 pounds per square inch. So that is the stress that's internally inside that post. So now what you want to do, I'm just going to mention this now, and this will come up later. FC or FT, normal stress in compression or normal stress in tension, your calculated, this is your calculated, has to be less than or equal to your FC allowable. And we'll talk about that later. Allowable is that allowable stress from design charts, from lumber manuals, that's allow to hold that stress without breaking it with a factor of safety, and we'll talk about that more. So this is key. So this is calculated, has to be less than the allowable by code. This typically you find these in code values. Okay, so that's important. So that's how you calculate stress. Force P divided by area. It's C if it's squishing, T if it's pulling apart. Okay, because if I look here, if I look at my senses here, the senses are going towards each other. So that means this fir, this Doug fir post is being squished in compression. So that's that example. All right, let's do a tensile example. A steel rod with a diameter of 15 millimeters supports a weight equal to 6 kilonewtons. Determine the average unit tensile stress developed in the rod. Okay, all right, so with that, so we know it's P divided by area, except we're pulling it. Okay, we are pulling it. So 1, we know P equals 6 kilonewton. 2, we know area equals 15 millimeters, but that's not an area actually, right? That is a diameter. Okay, so we got to go pi times d squared over 4 or pi r squared. Okay, so how does where does this pi d squared over 4? So if I know, I'm just going to derive this for you. If I know d over 2 equals r, if I plug that into pi times, substitute d over 2 for r, d over 2 squared, I get pi d times d, doing algebra, is squared. 2 squared is 4. So this is pi over 1. So that's where I get pi d squared over 4. So I'm just substituting d over 2 for r because it gives you the diameter in millimeters. It's just easier to work in diameters. You don't go to a hardware store and ask for a 7.5 millimeter radius pipe. You always ask for it in diameters. Okay, so with that, pi times 15 millimeters, and we're going to square that, divided by 4. So my area of my rod, steel rod, okay, is, so I'm going to take pi times 15 squared divided by 4. I get 176.7 square millimeters. Millimeters squared is my area. Okay. All right. So with that, but we have a unit conversion going on here. Okay. Kilonewtons, this has to actually be in meters, kilonewtons per meter squared. So how can I convert that? So I can take 176.7 millimeters squared times 1 meter equals 1,000 millimeters, and I gotta square that, right? Okay, so basically I can do that, or I can convert this value into meters right away. So let's see if we get the same answer. So 176.7 divided by 1,000 squared, and I get 0.000171767 meters squared. So metric's a little tricky. Or, oops, sorry about that. Or let's take 15 millimeters and turn that into meters. So I'm going to take pi times, so there's 1,000 millimeters per meter. So basically I got to move the decimal place times 0.015, right? 1, 2, 3. I square that and divide it by 4. I can get the same answer. 0.015 squared times pi divided by 4. And I get the exact same answer, 0.00167. Okay, so with that, now we know. So I just, hopefully you find value of me going through different various calculations here. We know the stress in tension equals P divided by area. And that equals, so we have 6 kilonewtons divided by 0.0001767 meters squared. Okay. And that equals, so 6 divided by 0.0001767, I get 33,956. 33,956 kilonewtons per square meter. That is the tensile stress in my steel rod. So believe it or not, that also, if I just, this also equals 33.956 megapascals. So there's some unit conversions there. Just wanted to throw a metric one out there for you. Okay, but remember, force is in normal stress. It's either in tensile or compression. The area is perpendicular to the load. Okay, so that's that example. All right, moving on. Shear stress. Now let's talk about shear stress. So V stands for shear. So it's F stands for stress, lowercase f stands for stress, V stands for shear now. So you have a T, a C, and a V. So those subscripts are telling you what kind of stress it is. Is it normal stress or is it shear stress? Or Greek letter tau. That's a tau. Okay. Load, applied force for load, and this time the area is parallel. So this is my little parallel sign right there to the load. So if I look here, right here, that load, remember what a parallel line is? The load, see, the line of action is parallel to that shear surface, as you can see it right here. So it has to shear off. Okay, the units are the same in metric or in English. Okay, that's the difference. Shear stress. Remember, load is parallel to the area. I'm shearing things. You're gluing two things together. Okay, that's the key to difference between the two. All right, let's do an example. A plywood fabricator uses an arrangement shown to determine the shear strength of a glued joint. If P equals 3,000 at failure, what is the unit shearing stress that develops between the plywood pieces? Okay, so we have P equals, that's my load, 3,000 pounds. Now, area has to be parallel. Now, let's talk about this. So, I'm going to do this in red. So, right here, would you agree we have an area here and an area here? There's two areas. So, what you got to do is you got to kind of look at these problems. Could you assume if everything was uniform and equally loaded, would you say half the load is held by this plane, this shear plane, and half the load is held by this shear plane? The answer is yes. So literally, I got to count the sort of 3,000 pounds is held out by this area right here. So if these two area, one, and then this one in the background here. So that 3,000 pounds is held by two areas. So basically what I got to do is I got to double the area because it's being held, okay? Or I can take one area and divide by half of the pounds and you get the exact same answer, and I'll show you that, okay? So we know, all right, so we know this is 3 inches high. So let's get our dimensions here so we know what our area is going to be. So we know it's 2 inches here. We know it's 1 inches up. We know that's 3 inches. So would you agree it's 2 inches by 2 inches? Would you agree? Right? So 2 inches wide by 2 inches deep because it's up 1 inch from 3. So my area is 2 inches by 2 inches, which equals 4 square inches, one side. Okay? Times 2, that means I have total of 8 square inches of area total. Okay, so my shear force, F is stress, V stands for shear, equals P divided by my area parallel. Okay, so with that, I have 3,000 pounds divided by 8 square inches, because remember it's holding up two areas. So 3,000 divided by 8 is 375 pounds per square inch. So that's the shear force that develops between the plywood pieces. Okay. Now, that assuming two sides. Now let's do it. Half of the load, 1,500 pounds, is only holding half one side of it. Divided by 4 square inches, and I get 1,500 divided by 4, and I get 375 pounds per square inch. Okay, same thing. So that's something just to keep in mind, how many areas I have. And remember that load is parallel. So parallel to the load vector. Okay, so that's that. That's shear stress. Okay, so when I look here, when you look at a bolt, so FV single shear, we have P over A. So when I look here, for this bolt to fail, it has to, that shear has to show. Area A is the cross-sectional area of the bolt. Okay, so that's how these two would shear apart. So that's why you need to know shear forces so you can size the bolts. So that's why you have really big bolts in bridges, because there's a lot of shear force there. So that's a single shear. Now if we go to double shear, okay, we have this area and this area. Okay, the total load is here, is held up by two areas. Half the load is on this area and half the load is on that bolt area. Okay, so I kind of like this picture, kind of explains it. So you just understand what's going on here. You got to make sure you have enough area. So this, I like this example here. Okay, so like when you're bolting trusses together, steel members, etc. So this is key. So something to keep in mind: single shear, double shear. Okay. Now knowing that, let's do an example. Okay. All right, so determine the shear stress developed in the bolts shown in the lap splice if the applied load is P equals 8 kips. So P equals 8 kips, or there's 1,000 pounds per kip, so that's 8,000 pounds, either one. Okay, so we have 8 kips there, and we also have 8 kips here. So now we have 2 5/8 inch diameter bolts. Okay, so we have a shear area there and a shear area there. So would you agree the 8 kips is held by 2 bolt cross-sectional areas of bolts, or half the load? We can assume that half the load is taken up by this bolt and half the load is taken up by that bolt. So either way, I can divide the load in half and do one area, or take the full load divided by 2 areas. Okay, so area. So remember, it's the cross-sectional area, and that's cross-sectional area will be parallel to that bolt face, equals, so 2 5/8 inches. So 5/8, let's turn that into decimals of inch. 5 divided by 8, I can't remember, is 0.625. So 2.625 inches squared. We're going to multiply that times pi, and we're going to divide that whole thing by 4 to get my area. So that's the area per bolt. So 2.625 squared times pi divided by 4, and I get 5.41 square inches per bolt. Okay? So let's calculate the shear in each bolt. So I'm just going to assume one bolt, half the load. So F prime V equals P divided by area, which is parallel to that load, which is the cross-sectional area of our bolt. And that equals, so half the load, 4,000 pounds, divided by 5.41 square inches, and I get 4,000 divided by 5.41. And I get 739 let's see, 739.37, so 740 PSI, okay, equals F shear stress. So the maximum shear stress that the bolts are capable of safely resisting is equal to 14.5 KSI. Okay, so this, if I want to turn that back into, so this is 0.74 KSI. I just moved the decimal back 3 spots, 1, 2, 3. Okay, so F prime V has to be less than F prime V allow. So would you agree 0.74 KSI is less than 14.5 KSI? And that is true. So we are safe with that. Okay? All right. So, now we're into design mode. Okay? So where do these loads come from? Load tracing. All right, let's talk about bearing stress. So just another, stress is stress. So remember that bearing pressure that you were dealing with in Learning Plan 1, Chapter 4, load tracing, that is a bearing stress. So that bearing capacity is actually a bearing stress, an allowable bearing stress. Okay, so those loads that we end up with from the load tracing have to be less than our allowable bearing stress. Okay, so that's why that load tracing number, that final load on top of your foundations, are the numbers that you give to the geotechnical engineer, and we got to design a foundation to work. We got that determines the size of your footing. So it's my recommendation that you get us geotechnical engineers involved early, because what happens if I can't put it on a shallow foundation? I have to put it on a deep foundation. Your design is going to change. Okay, so unfortunately, you got to kind of go through the load tracing. Here's my preliminary design, and then I'm going to look, okay, the site that I want to build on, you want to do some soil borings, and we want to see, okay, based on the size of the structure and the loads of the structure, will this foundation work? Because it would really, I've seen it where the architects have gone through, sized their footings, and then they want to build this house or structure, or commercial building, whatever it is, and I had to tell them, sorry, we cannot put this on shallow foundations. We have to go to deep foundations. So they basically have to redesign everything. So it's very important that you get civil engineers involved in your site process, especially geotechs. Okay, so that's my soapbox talk today. All right, so bearing stress. P stands for bearing in your textbook, okay? So it is a normal stress because the load is perpendicular to the area, okay? So it's a normal stress. So FP equals P over A, okay? Just terminology. All right, let's do this problem, okay? A W12 by 87 steel column, 10 feet tall, is subject to a load of 360 kips. Okay, here's our P. The cross-sectional area of the column measures 25.6 square inches. So usually you can find that from steel tables, and you actually have those in your book. Determine the following. The compression stress developed in the column, A. The bearing stress between the steel base plate and the concrete footing, so that's right there. The bearing pressure stress between the base of the concrete footing and the soil. So that's right there. Okay, so let's do A. I just got another page here. So A, so the, whoa, that's a ugly looking A there. All right, A. Bearing stress, so I'm going to reread it so I don't make a mistake. The compressive stress developed in the column. Okay, so P over A perpendicular compressive stress. Remember, compressive stress and tensile stress are normal stresses. Perpendicular equals F C, and then I like to do this, column, right? So you know what I'm calculating. Okay, so we know P equals 360 kips divided by the area. Okay, area. Area is 25.6 square inches of steel. And again, I can find that in a steel, in tables. 25.6, right? Okay. 25.6 P, oops, that's square inches. Okay, now if I do my math, 360 divided by 25.6, I get 14.06. I'm going to say 14.1 KSI. Now, if I look over here, it says Fy, my yield stress, it doesn't matter if it's in compression or tension, is 50 KSI. Okay, so if I go to this big picture, so Y stands for yield, and we talk about that in lecture part 2. That is basically when that thing starts yielding, like deforming, and that's a design limit in which I'll be talking about. So F stands for stress, okay? So it can handle up to 50 KSI before it starts yielding, and we don't want yielding. So that means, and this is a steel strength number, and this is a column shape, that means we are less than or equal to 50 KSI. I'm kind of adding a little thing to this problem, and so that means we're good. So this is my answer. The compressive stress in the steel column is 14.1 KSI. So that answered A. Let's go to B. The bearing stress between the steel base plate and the concrete footing. Okay, so that's right there. All right. So we have 360 kips, but we also have this weight of the steel. Okay, so B, we need to add, so so bearing, so F, P, I'm going to say plate, bearing stress, plate, equals P divided by the area perpendicular. Okay, so our P equals 360 kips, but we have to add the weight of the steel. Okay, so if you go into your textbooks and somewhere, let's see, I can tell you. So I'm going to go to your textbook, and there is a chart in here somewhere in chapter 5 that gives you unit weights of materials. All right, that's not it. It's here somewhere. There it is. Okay, so I'm on page 278, and we have density, says unit weight density gamma PFC, which I'm thinking they're saying pounds per foot cube, but it's pounds per cubic foot. I look at steel, and it weighs 490 pounds per cubic foot. Okay, so I'm going to do this off to the side here. So I know steel weighs 490 pounds per cubic foot. But I need it in pounds, right? So pounds per cubic foot. Okay, so we have an area of 25.6 square inches times 1, we got to get this in square feet, equals 144 square inches, because 12 times 12 is 144. So I'm going to take 25.6 and divide it by 144, and I get 0.178 square feet. And the length is 10 feet. Okay, so we go 0.178 square feet times, it's 10 feet long, times 490 pounds per cubic foot. So all of these get canceled out. So if we take 0.178 times 10 times 490, that thing weighs 872.2 pounds. So this is 872.2 pounds. So I'm going to, okay. Now this is pounds. So sorry, this is a little messy. I got to get that in kips. So that is, I just slide this over like that. So P, let's go back to P for my bearing stress, equals 360 kips plus 0.872 kips, and that equals 0.872 plus 360. I get 360.9 kips, rounded up, right? So P equals 360.9 kips. Okay, so now our area is, the plate is 18 inches by 18 inches. Okay, so 18 squared, and that's 324 square inches. So our FP of the bearing plate is 360.9 kips divided by 324 square inches. Okay, 360.9 divided by 324, I get 1.11 kips per square inch. 1.1 kips per KSI, kips per square inch. So that is the bearing stress at the bottom of that plate. So why is that important? So there is, you can only sometimes, you don't, what could happen is you can actually punch this steel column into the concrete. The surface concrete can't hold that much surface stress. So that's why you have to put plates on the bottom, so we don't basically shove that column into the concrete. Okay? So that was B. This is the answer for B. So a little longer than I expected. So remember, we have to add the weight of the steel. Weight of steel weighs 490 pounds per cubic foot. It's 10 feet long. We know the area is 0.178 square feet by converting it. Turn that back into kips. We add it to 360 kips. Divided by my plate area, I get 1.1 KSI. Okay, so that was answers for B. All right, C, will come over here so I have enough room. C is what? Oops. Bearing pressure stress between the base of the concrete footing and the soil. Okay, so now we got to add the weight of the concrete here. Oh boy. All right, so units. We don't. It's 7'6" by 7'6" by 16 inches times 150 pounds per cubic foot. Okay. They'll give us a load in pounds or pounds per cubic, okay, in pounds. But if we know it's in pounds per cubic foot, if we take it times the height of the pound, that gets in pounds per square foot. We can just add that to can we add that to the previous stress? No, we cannot. But we know our area is here. Okay, so let me back up on that. All right, same principle here. FP soil equals P divided by area perpendicular. Okay, P equals, so we know the weight of the load on top of the column plus the load of the column is 360.9 kips. We determined that from problem B, 360.9 kips. Now we got to get the weight of the concrete plus 150 pounds per cubic foot, 16 inches wide. It's 1.33 feet. Okay, times 7.5 squared. Oops, clear. 7.5 squared times 56.25 square feet. All right, and then we got to divide that whole answer divided by 1,000 to get it back into kips. So 150 times 1.33 times 56.25. Is that right? Let me try that again. 150 times 1.33 times 56.25. Yes, that is right. So that footing that is 16 inches high by 7 by 6, 7'6" by 7'6", and unit weight of concrete, reinforced concrete is 150 pounds weighs 11,221 pounds. Okay, I'm going to divide that by 1,000, and I get 11.2 kips. So I'm going to add 11.2 kips to the total weight that's seen on that soil. Okay, so if we go, so P equals 360.9 kips plus 11.2 kips, and that equals 11.2 plus 360.9. Oops. There's more than one way to solve this problem. I'm just doing it 372.1 kips. Oops. Okay, kips. Area equals, so now that weight is spread over the area, the bottom area of this footing, which is 7.5 feet times 7.5 feet, which is this guy. 7.5 times, I just want to double check my numbers. 7.5 squared, yep, 56.25 square feet. So the bearing stress on the soil equals 372.1 kips divided by 56.25 square feet. We usually deal in bearing pressure on your soil in square feet instead of square inches. Materials like steel and wood are usually in pounds per square inch. So 372.1 divided by 56.25. and I get 6.61, so 6.62. 6.62 kips per square foot, or that's over 6,000 pounds per square foot, almost 7,000 pounds per square foot of pressure underneath that footing. Okay, that answers C. That is a very high number, by the way. So that footing will actually have to be bigger. So typically, soils around Green Bay, we can maybe go up to 5 kips per square foot. So we'd have to make that footing much larger to get it less than 5 kips per square foot, or sometimes we even go to 4 kips per square foot because we have to be concerned with settlement. Okay, so all right, so basically that's kind of how it works. So typically I give you this number, I give you the allowable. Again, we want to check, is this less than or equal to FP allow? If it's not, we're going to set FP allow to 4 kips per square foot. My load doesn't change, so I can just basically do algebra and calculate a new area and then take the square root of that, and that'll give me my new size of my footing, so I don't exceed my allowable bearing pressure, so I don't cause a bearing capacity failure, and I control my settlement. So this is very important that you kind of under the foundation part is what us geotechnical engineers are needed for, and to help you so you have a successful structure that stays serviceable, because you don't want things settling and your doors don't open, windows start cracking. Okay. All right. So basically, different forms of the stress equation. I kind of talked about this. Shear stress, V, P over A. So if you need to, we can rearrange that equation. If I know the allowable shear stress, and if I know the load that I need to do, I can back calculate an area. Okay, so you can rearrange this, or right, and so that's kind of what it does. So this is, and I kind of mentioned that before, this is applicable to normal, shear, and bearing stress. If I know one thing, or if I have allowable design values, I can back calculate what's needed for that area. Or if I have like a remodeling project, if I have an allowable stress and I have an existing area of a column in a house and they want to add a third story, then I can back calculate what's my allowable load on that. Okay, and then if my addition on that column exceeds that, then I have to make a bigger column or remove it or double it up or etc. Okay. All right, let's talk about strain. Strain, this is epsilon, this is delta. So epsilon, this is delta, oops, okay, this is delta, or change. You've probably seen this, the triangle. This is length, okay? Strain is how much it deforms, okay? Delta, total deformation, elongation, or contraction. So tensile strain, stretching, compressive strain, squishing. So before we were measuring the stress, now we're measuring how much it deforms, the strain rate. So they call strain. It's related to deformation, okay? So L is the length of the specimen in the load direction, okay? So when we put a load on it, it's going to stretch. So when we put that load on it, it's going to stretch. So if we put a load on it, it's going to shrink, okay? 2 examples. So let's do a quick example. So let's say my P is 10 kips and my original length equals 10 feet. Okay. I can measure, my original length is 10 feet and my deformation is, I'd say 0.25 feet. So if I calculate the strain in that, strain equals deformation divided by original length. Okay, so I don't need my p-value, right? So strain is a function of the load. So if I have a larger load, obviously I'm going to get more strain, so that strain rate's going to change. So if I go 0.25 feet and I divide by the original length of 10 feet, so it's important, this has to be inches per inches, millimeters per millimeters, meters per meters. It's a unitless number, okay? Strain is a unitless number. So if I take 0.25 divided by 10, my strain rate is 0.025 feet per foot, and those cancel out. So basically that's saying of a load of 10 kips, I'm just making these numbers up, is that thing per foot of length of that steel bar, it's going to strain 0.025 feet. Okay? So that's kind of what it means. So we can rearrange these equations. If I give you a strain rate and I give you a length, I can give you the deformation. Okay? So you can rearrange that equation. All right, let's do compressive strain. So we know epsilon strain equals, oops, sorry. This is my little crazy delta thing here. Delta over length. Okay? Let's say I give you a strain rate of 0.001 inches per inch. Concrete cylinder in compression. Okay? The original length of my cylinder is 12 inches. Okay? I want to know what is my deformation of that cylinder. So I can take length times epsilon, and that'll give me my deformation. So if I do that, that equals, so length is 12 inches times 0.001 inches per inch, right? Because remember, this is inches, this unit is inches here. My answer is in inches. So if I take 12 times 0.001, so that thing, my concrete cylinder deforms 0.012 inches, and that equals my deformation. Okay, so why is this important? Why do you need to understand strain? So just remember, strain is change in length over the original length. Every material has a different strain rate, so this is why we use steel versus aluminum versus wood versus concrete. We need to know that because we need to know how it deflects, basically changes shape when we put a compressive load on. If our strain rate is too high, we'll have some performance issue, or if it stretches too long. Okay, so that's why certain materials are used in certain situations, because we can't have that strain rate. So this is a very fundamental practice here, and I'll go over more of this in lecture 2. Okay, so all right, so basically why strain is important. To get strain, we have to have stress. No stress, no strain, no strain, no stress. So if I look at this problem here, P divided by area perpendicular, right? If I have P of 10,000 pounds, and then this is a 6-inch diameter cylinder, that stress is causing that strain. You got to have stress to have strain. So these stress and strain are related very closely. Okay, so you can't have one without the other. Does that make sense? Okay, and we'll go over this in part 2 lecture. All right. So that's stress and strain. Okay. So basically, here's your assignment. Read pages 251 to 266 of your textbook. Work through the example problems. Try to get these symbols in your head. Work these problems in the textbook. Okay. Remember, you have the solutions menu in Blackboard. Don't just try to figure out the problems and see if your answer is correct. If you get the wrong answer, redo the problem until you get the problem right without having to look at the steps. If you have not done that much, you don't understand the material. So it's concept. Just remember that formula. F equals P over A. Just identify, is it compression, is it tension, or is it shear? You can rearrange that equation. Find your load, find your area, you can calculate stress, or vice versa. All you're doing is rearranging that equation. It's simple algebra. Strain, epsilon equals change in length over length. I have to give you two of the three variables in that equation to make it solvable. So it's hopefully that helps you get through this, okay? So thank you for your attention, and I will record part 2 soon, as soon as I figure out how to turn this thing off.